Hi, my name is Jacobo, and I, along with Albin, Korawich, and Guillermo, form the Ride Comfort team. There are many travel options to and from the CMU Pittsburgh campus. Proximity to campus, type of transportation, and budget all factor into how one gets to campus. While a car might save time, riding the bus could save money. A critical aspect that is not easily quantifiable is comfort. Measuring comfort is crucial for one to fully understand the range of advantages and disadvantages of most transportation alternatives. Our objectives was to better estimate comfort through different related variables. Outcomes help better determine pros and cons of different transportation types. We were able to find gaps in accessibility of transportation to campus when a vehicle, bike, or scooter is not an option.
And we're going to be looking at a few primary phenomena, that's noise, vibrations, and temperature and humidity. And these are going to be sensed with the microphone, accelerometer, and a temperature and humidity sensor. So the first one we're going to be looking at is temperature and humidity. And this is actually a pretty static signal, so we can sample at a very low frequency and still obtain accurate results. And ultimately we'll be looking at this published kind of human comfort range for temperature and humidity. That's between 22 and 27 degrees C and between 40 and 60% relative humidity. Anything outside that range will be perceived as discomfort. So secondly, we'll be looking at the vibrations and movement. And this is very important because we're looking at how kind of bumpy the ride is and trying to quantify how uncomfortable it is from that perspective. And so we're only going to be using the z-axis of the accelerometer, which we calibrated to 1G. That will be sensed and compared for each mode of transportation as well. And then finally, we'll be looking at sound and noise. And once again, we'll be obtaining values strictly in amplitude of sound because we can't sample at a high enough frequency to actually obtain the frequency of sound waves. And so we'll be comparing the amplitude of sound, which is measured in decibels, with these kind of published thresholds. Namely, 120 decibels or higher would actually be perceived as painful and very uncomfortable. Normal speech is around 60 decibels. So we'll be looking for those as well.
As you can see, this is our final setup of the Raspberry Pi. We have all three sensors connected on the breadboard. For the vibration and sound, this is connected to the AD converter, but for the humidity and temperature, this is connected to Raspberry Pi pin because the output is already in digital. Here we have the actual physical button. When we go out and collect the data, we can use the button to start recording the data, and when we reach the final destination, we can press the button again to stop the recording. The detail of the code is already uploaded into our GitHub page. If you're interested, please see the link in the GitHub page on the top. The main code for running the data collection process is the smart_comfort.py. The above three code here, they are for testing the functionality of the sensors. This th11.py is the function that's necessary for running the smart_comfort. There is also another video demonstrating how we actually did it on the day that we collect the data. If you are interested, please click the link in the video description.
So if we see the results of the experiment, first we have the results of the noise, and here's the plot of the decibels in the domain of time of the three transportation methods. But nothing very useful can be obtained from this plot because it's very noisy and the values go beyond the limits of the plot. So what we did was to obtain the plot of a 20-second window moving average of the decibels to better understand the trend of this. So then the dashed lines represent the average of each measurement, and it can be seen that the bus and the scooters are the loudest transportation methods compared with the car. Then if we analyze the vibrations, we have the plot of the acceleration and the time, and it can be seen here. The dashed line represents the deviation from 0G, which is believed to be the most comfortable zone to be in. And the scooter is the one that deviates more from this comfort zone. With respect to the humidity, here the dashed line represents the average of each measurement, and the red line represents the comfort zone that we defined. So the scooter is the one that is more deviated from this comfort zone. Then if we analyze the temperature, again the dashed line represents the average. The scooter is again the one that deviates more from the comfort zone. So finally, we calculated the root mean square deviation of each trend with respect to our comfort zone parameter for each measurement. So if we see acceleration, the car is the one most comfortable. Then if we analyze the noise, again, the car is the most comfortable. The temperature, the car, and then humidity, again, the car. So if we summarize in this competition who won, the first place is for the car, the second place is for the bus, and the third place is for the scooter.